Okay. All right. So welcome back, and today we're going to talk about operating systems structures. So, and a little bit of a history. All right. So last session we covered course logistics, and we talked about what is an OS in general, what does an OS do, and the goals for an OS from different perspective of the user and the designer, right? And also we talked a little bit about Pintos. So if you have any questions or missing anything, just shoot it before we start today's lesson. All fine? All right, great. So we also had a few assignments for everyone. Who has downloaded and installed VirtualBox successfully? Just raise your arm or your hand. Pretty good. If not, it's kind of late, so do it. We've had some students having issues with their computers, so they're resolving it with TAs, all right? Piazza, I hope everyone is already joining Piazza. Is there anyone who is not there in the Piazza in the class? If so, just do it, because we just like posting updates and announcement there. Yep. So this was also the reading chapter. I hope some did. Who has already finalized their groups? Raise your hand. Okay, half of the class, less than half of the class. Please do it again by the end of this week, all right? So today we're going to talk about some brief history of computer architecture. This is kind of like subjective. This is something that I thought that would be interesting, to put, just to, give you a little bit of food for thought. And we're going to talk about major OS components and OS design approaches, right? So this first, we're going to start with the history. All right. So computer architecture, when you think about it, so everything is down to the wire, right? So chips, motherboards, whatever, hard disk, and everything is basically some hardware. And those hardwares, you understand that there are electronics going on, and there is, some design. But how does it do it? Like, if you really think about it, how does it do? When you open up your computer, when you're like, playing music, doing something like drawing, playing a game, and then there is like, I don't know, AI agents in the game, whatever. How does it eventually doing it with that, hard wires? Like everything is connected. It's not that, something is physically changing the structure in real time. So where does the complication come from? If everything is hardwired in the, down there, where does the complication come from, and how does it know? So for example, if an OS wants to, schedule different programs, if your program wants to do update, or I don't know, a game is a good example. It's very interactive. How does it know? Like, just make a guess. Try to, like, I mean, it is running a program is the general answer. But yeah, go ahead. An event loop? How is that? What's that? Okay. Okay, but how does it know an event has happened in the first place? GPIO wires. Okay. That usually is to do with actual hardware. The game actually is not. I mean, your actions are something that tell the computer something has happened. But what about the agents themselves, like the players in the game? Is it interrupt? So again, interrupts are something on the same line, which we're going to talk about briefly today. But again, even the computer agents themselves, they like, how are they? That's still higher level than, It's just like that. We're going to go through an example here, and so it just gives you an idea that the complication actually is not coming from anywhere. Like, it's very simple. It's just like builds upon itself, right? So if you think about biology, so you have adenine, thymine, and guanine and cytosine in your DNA, right? These are just like molecules, right? These are very simple molecules, right? Do you think they're like, is any of them smart? Do they do anything? Do they change formation or anything? I mean, I hope you have like taken some biology class, right? So no, they're just like molecules, right? And if you just, form them like DNA, it's just like pretty stable, right? considering the environment, harsh environment and everything, they're pretty stable. And they, again, don't change. They don't do anything. They're just there, right? So that's the hardwire that we talk about, right? But given the environment, again, I don't know how the first cell, got formed, but given the correct environment, the DNA using, generates itself with some proteins and RNA, and then the RNA now creates the other proteins, and these proteins, again, they're still very, very complex molecules, but they're just there. Like they don't have anything, like they don't think. But when you put all of them together, a huge step forward, you have a living cell. The proteins are just like floating around, and then acting upon some other molecules, and then the membranes, and then some of them absorb food, and then the food keeps the environment stable, and then there's I'm going to read it. It's not important, but so they're nucleus, and then there's cytoplasm, hanging, and then there's a Golgi body, whatever. All these parts come from nothing. They were just this, right? So where did the complication come from, right? Again, we're just not talking. This is not a biology class, right? But so given the circumstances, it's amazing. It's amazing if you think about mitosis or meiosis, the cell division. How does it know, really? This cell is just there. It doesn't know if there is surrounded by other cells. Is it I don't know, in space, whatever. It doesn't feel gravity, I suppose. But at some point, it just decides, okay, I have to divide, right? And then it just nucleus goes away, the chromosome comes out, and then for some reason they have a beautiful formation here, and then they just separate away from each other like that, and then it just divides just like that. And here you can see the image, right? So how does it know? Why do these go away? Why they don't go together to one side, or I don't know, different sides? It just, if you think about it, how does it know? I guess it doesn't. It just happens, right? And again, it has happened because of the complication that has formed with all those proteins and DNAs, right? So it's a bit similar, but somewhat also different with the computer, because the computer was built purposefully, right? It was not that different formations were tried and then, hey, it's now working, right? And it's running a game. So it was not like that, natural selection. So we had electronics, which you already know. We have power supply, we have resistance, we have inductance, we have capacitance, and current goes through it. And well, there are fascinating things going on with electronics. I mean, at least it was back before the transistors, right? But they couldn't make computers out of that, right? So in 1947, doesn't matter, transistors were created, right? Not just FETs, but original transistors using semiconductors, NPN or PNP. And well, this is different because it gives you a gate, right, where you can control the flow of current from here to here, right? And that's somewhat gives, again, a bit of a control that can be hardwired itself, okay? So then you have a control that you can turn a switch. This is a simplified, but it's a switch. You can turn it on or off, right? And then this now can be, again, a gate to another one, and another one, and another one, right? These can be all hardwired. And when you look at it, next thing, you have a formation of these going toward the digital era, and then you create out of transistors all the logic gates, right? I think you understand how the logic gates work. They're somewhat in digital, meaning we have an on and off states from now on, and not analog. And you have all these different gates made from them, which is an OR, AND, XOR, NOR, NAND, NOT. Basically gives you the control. So your output will be on if either of these are on, if both of them are on, if only one of them are on, if only if none of them are on, not only if both of them are on, and so it gives you different flexibility, right? So with a smart formation of these gates, you create a latch, and this is fascinating because it doesn't actually have a one-directional flow of your signals. which you think that, hey, this is the input, this is output, this is input and output, output of this is the input of that, and then so on. But it kind of like has a formation of like looping, right? You can see how it works. And so it's very simple. And this is an implementation with NOR. And what does, it's called an SR latch because it has a set and reset. So you have two signals, set and reset. And if you don't signal any of them, there's no change. It basically preserves the current state. And Q and Q bar are, you know, the reverse of each other, and then basically feeding them to the opposite input. So if you enforce a set, then give it like a, you know, very short, brief amount of time, and then the latch will be set. So then it will ensure that this will be on. And then again, if you go back to 0, 0, it just like stays there, you know, for how long you want. And then you signal it reset, and then it goes to 0 and forces it as 0, right? So you have a control. I want to set it or I want to reset it. And there is also an invalid condition depending on the, I think, how the implementation is. This can be, but it should be avoided basically, right? So you take the same latch over there, you put like these behind them, and then now you have a gated D latch. And it's the data that you basically want to store, and you have a gate, meaning if you open it, the data flows in, and then will be stored in this, and then if you close the gate, no matter what to do with this, it's not going to change, right? Because as you can see, this is an AND, this is an AND, so if the gate is 0, this and this will be 0, so it will be a 0, 0 SR latch, nothing changes. So the gate, you have a control of the gate, and as long as the gate is open, whatever the data comes, it goes through, you know, and then basically, if you close the gate, nothing will change it, right? So now this is a block because now you can store your data and, you know, store it. You can control that using this, right? So now you have a memory cell basically, right? Because you can store it. Again, like signal is coming, you have like a brief moment, you catch it and then store it for how long you want, okay? So you take a couple of these together and, you know, connect them in this way. Again, these are just design. You don't have to know why, but this is how it works, right? Now you have a clock instead of a gate that if it's open, anything happening to D will show up in the output, right? If you open the gate and the D bounces between 0 and 1 like so many times, the output also does that. Maybe you don't want that, right? Maybe you want a stable, clean output. So using this formation and a clock, instead of like opening a gate, you only gate or basically allow data on an edge of a clock. So if your clock is a signal, a periodic signal that goes up and down just like that, which is easy to generate, in this case, on a falling edge of the clock, whatever is the status of the data will be stored, and that will be stored till the next falling edge of the clock, no matter what is happening like for the data. On the falling edge of each clock, you are sampling the data and then storing it there on the output, right? So this case, there's not the line should be here, but then basically that just brings it down, right? The same goes, you know, as. So now basically you have a controlled flow of data because now you have a control, which is that clock, which is periodic, right? And then now you can interconnect all these outputs to inputs and outputs and inputs to outputs, right? And you create stuff. So you create shift registers, you create, you know, ALUs, and then basically next step we're going to go for processors, right? So these just like build upon, you know, each other. So again, if you look at it, they're just like doing nothing. The input is coming, the clock is going, the data is flowing, right? But basically, one of the important things that you can do is using these and the gates, again, you can create decoders. So if I have you know, a byte, like 8 bits, right? You can have a decoder hardwired that, okay, if I give these zeros and ones to the decoder, this will just have this output. And then that output might be larger, right? It might be smaller. It doesn't matter. But then it's instance. You give it 1 byte, it just instantly give you, I don't know, other formation, which is decoding. And now that decoding can basically signal different things, right? I'm going towards the instructions, right? So if you give an instruction, how does it know what is that instruction? How does it know if I have to add, multiply, subtract, what to do? How does it decode? That's next. So computer architecture architectures. Basically, there were two general architectures. One was von Neumann and the other one was Harvard. They had like subtle differences. It doesn't matter why this one, stayed dominant, but that's what it is now. And so it defines as we have a central processing unit which controls and does the arithmetic logic processes. And then there is a memory unit in that this should be connected to, which stores the instructions as well as data. The hardware architecture separated these two, right? This is how it is, and we have obviously input and output, which ensures what we want to do with them. So the architecture of Intel 8085 was a huge, I think, a step and towards whatever that computers are doing right now, and that is sorry. So the memory, and this is the whole processing unit only. There are buses that this connects it to memory, and there are a bunch of registers here. There are general registers. There is a stack pointer, program counter. There is instruction registers, which once you load the instruction from memory, you store it there again for as long as you want. There is the decoder that I just said. The decoder tells what this instruction is actually, and give the timing and control. So if it's an instruction for add, then it will give the signal to the correct gates, basically, to hey, you should add, or basically the add circuit should be on. If it's a multiplication instruction, then it will signal that the add circuit should be off, the multiplication circuit should be on, right? So this is what it does. And then after the whatever the multiplication or addition or whatever, the result is stored in a flag register, and there are the accumulators, the register that everything is happening in that, and then you have buffers and everything. So it's packed, but this was I think we can say maybe a mother of the current architectures. This is basically the father of 8086, which you hear everywhere like x86, because everything is now compatible with x86. That's just I guess what's the business and marketing side of it. You can't just change the whole computer architecture because people have paid for them, right? So they don't go to your architecture if they can't use their previous softwares. So, and this was the father of 8086. So. So there are important components in this. The program counter, which basically tells you where you in memory is your next instruction that you should read. You meaning CPU, right? And then there's the instruction register and decoder, which then takes that it basically loads that from memory and decodes what it is and what it should be done in the next few cycles of the clock. ALU is everything is happening there, meaning if you have a addition of two registers, it will happen in the ALU and everything. The flag register stores the result. The result is not the addition itself, but for example, if the result is negative, we don't have negative or positive numbers, right? If it's negative, there will be a bit in the flag register. If you divide by 0, the flag register stores it, or if it overflows in the number of bits. If it's there are tons of things in the flag registers that it's just stores it. The general registers that the CPU itself uses, or you can use. So you have instruction to add B and C. There is another instruction that add B and D. There is another instruction to add C and D. Right? These are all registers, and then the reason is you want to have as much flexibility, and you want it to happen quick, right? So that's why you have different instructions that instantly they run, and then they give you results, right? And this basically allows much faster. We have CPU processors with less registers and more registers. Obviously, more registers allow you to do more stuff quickly. You have a stack pointer. A stack is I'm sure you're familiar with what a stack is, but the design of a stack, why a stack is needed, is very important. We're going to talk about it in your project 2. Till then, you don't need it. But to use a stack, you always need to know what is your latest, your head in the stack, basically, right? And there is the interrupt controller. So as you said, like interrupt is very important, because if everything is hardwired, then how does the flow stop or intervened? This happens through interrupts. This can be hardware interrupts, such as a timer that tells the CPU separately through a hardware that, hey, a millisecond has passed. Do you want to do something? Go for it. If you don't, just because the CPU itself doesn't feel time, right? It doesn't know. So the timer keeps ticking it. Hey, another millisecond. Hey, another millisecond, right? And then the CPU can check, oh, now, if this millisecond has passed, is it time to do these stuff or not yet? Is it time to do these stuff or not yet? This is a hint for your project number 1. So communication, things are happening in packets coming from network, right? Serial communication, Wi-Fi, whatever. All these happening, and then basically the Wi-Fi tells your CPU, hey, I have a packet ready, come and read it, right? So these are happening with control. Trap, if you divide by 0 or something needs to be done. And these, along with software interrupts, will be written as instructions. So in case a division by 0 has happened, do these instructions. In case, I don't know, like if you can also call interrupts yourself. That's the software interrupts. So if you call, if a user called interrupt number 34, this is what you want to do, because that will then be an agreement between an operating system and the user. All right? Any questions so far? Also, for those who are like, kind of closing your eyes, wake up. Okay? Oh, we're almost done with the history. If you don't like history, I didn't enjoy history. I mean, not this history, actual history. Any questions so far? No? All right. So execution steps, very simplified, is this. You fetch an instruction which is pointed by your program counter, and then that instruction comes into the decoder, and then this decodes the instruction, what is to be done in the next few cycles. Should I multiply? Should I add? Should I read another byte from memory? Whatever. And then that basically gets executed in the next few cycles with all those things that I showed you with decoders, the flip-flops, and the clock. And then once that is done, the timing also tells what it's done. If it's required, obviously it stores or reads some registers, and flags sets them. If it's required, depending on what the instruction was, it will write some memory addresses as well. Write this result, to this address. So that will also happen. And then increase program counter to point to the next instruction. So now will be next instruction, right? So this is just what the CPU does. The only thing the CPU does, right? Everything else should be basically put ahead of it, right? So think of these machines in factories. So this machine, like opens the box, and then this, I don't know, puts this in the box. This puts the lid in the box. I'm taking these, by the way, from different websites. I try to reference all of them just in case, but this is not trying to distribute anything. And then this one, for example, stacks them, right? So what happens if a box is too big here? What happens? Come on, one person.
Broken down into...
You can break the arm, right? What happens if the box comes a little bit later? Like instead of here, this box is here. What happens? It just doesn't do anything. It just puts it on the the rail here, and then it might actually get stuck, jammed this one, right? The same thing happens with this one. If it's too heavy or too, they don't think, they're just doing the instruction, right? That's the exact thing. So who ensures that these things are not happening? One is basically you regulate. Like you have like control over what's going on. You have like checks. You have emergencies, right? There is another person or a machine that basically ensures, right? If a machine puts them at the same interval, then this can also expect it at the same interval. If a human does that, they should ensure that everything is set, right? And that is exactly with the instructions. If a programmer wants to program, they have to ensure that their instructions are well established in the memory. That was really horrible and difficult. I mean, I have coded a little bit of machine code where you actually tell that this byte should be in this memory, and then you basically program the memory separately and then connect it to the CPU and reset it, and then expect it to work. It usually doesn't, right? Because you always mess up, right? One instruction is like 1 byte ahead, and everything just falls apart because you want it to add 4 and 3, and then it takes that 4 as an instruction. What is that for instruction? You don't know, right? It might just like, I don't know, restart. It just might, I don't know, format your hard drive, right? So, so this is the job of a programmer, and later on in the OS. The OS should ensure, that nothing is going wrong. So then you have like instruction sets that you should now tell, okay, what is the instruction, for example, for? You can tell from this, I don't know, adding 2 registers, I guess, and so on and so forth. So these are the instructions given to you. And then because you don't want to like mess up, then you create a program which is called, for example, assembler. You program it really well, and then try to ensure, instead of like actually people writing machine codes or punch cards, they write some semi-codes, and then at least it ensures that, hey, I'm gonna like take these, whatever you write, into machine code, and at least ensure that the offsets are correct, or so you don't mess up. If you say like copy, I'll take the copy instruction. You don't have to worry about and memorize all of it, right? So and then using assembly, you build up other compilers and so on and so forth, and now you have like functional programming and everything, right? But basically these are just like tools, programs helping programs. All right, so now the modern computer architecture is basically the same. It is a CPU. It has a cache to speed up, the memory. The data and instruction is happening again between the CPU and memory, just like that. It's obviously much, much larger. And you have devices in your computer that you have like interrupts and data between your CPU. And there's also a direct memory access. So not everything is done by a CPU. If your hard drive wants to copy itself, over something, memory. All right, so this is the general architecture so far. So what is the limitation of these? Only a single user at a time, right? Current architecture, you have, I guess, heard like boring stories of old people that use punch cards, right? So you have like a stack of punch cards and then wait for hours so that the job of like, I don't know, adding a couple of numbers, finish, right? And then next person would do, right? So each user will need to be independent and have a full stack of software. Again, you have nothing. You have to start from scratch and build everything, or maybe, you have some pieces of code, either you can copy or someone has it available, so you can just like at least, but again, you have to have all of it. Not just punch card, but even like, again, machine code or simple codes. Drivers, if you want to like work with any hardware, you have to have the drivers with them. If you mess up, it's your fault. If the hardware that you programmed is different than what it is right now on this computer, it doesn't work. It's your fault. It's your responsibility. Compilers, I/O, and everything, you have to have them, in your program. And each user have a full access, which is kind of like a protection and security issue, right? Again, you might mess up with some of the devices, all right? So the serial operation of early operating systems allowed different people at least to, one application at a time. But then the OS was a runtime library that provided some services and, code for the programs, and users would stand in line to use the computer. Again, similar to that, one at a time. And then they came batch systems, but then they wanted to keep the CPU busy by having queues instead of like, the OS would handle job after another instead of like humans, right? And so they would just submit their jobs and wait and wait and wait. Again, serial, right? That's bad because maybe my program is running too slow. Maybe my program is not utilizing the CPU enough, right? It's just like doing a lot of I/O. So the time sharing comes here and allows multiple users to use the computer at the same time, all right? So basically, it allows interactive performance. So when multiple programs are running at the same time, if a program is doing I/O, the other one also can interleave processing or I/O in them, right? And then obviously, as they become cheaper and faster, it becomes more important to optimize for user time rather than computer time, right? Right now, you cannot, keep a CPU busy with one task, 100%. Usually, that's the case. The CPU is too fast; it just does whatever you want to do, and then just like be free, right? So then you want to utilize the CPU time, and then make users happy, right? By running as many applications at the same time that the CPU can. So the CPU is busy, but you also don't have to wait for your mouse when you move it to see the pointer, right? So this is a graph for that. Like within 30 years, this is just a general idea of like how things grew up from processing and CPUs per computer and the price for what you pay for each the processing. Everything has gone up like multiple orders of magnitude. Disk capacity was, I guess, like in order of kilobytes or megabytes. The same goes with RAM. They have now gone up much more. Internets, and also the ratio of users to computers, like they had like 100 users per one computer. Now you might have like 2 phones and 2 laptops and a desktop and everything, right? So yeah, this was the brief history, right? Any questions in that? Was it interesting? No, seriously, because otherwise I have to like reduce it. So now we're going to talk about the OS components, right? So these are now more relevant to what you're going to see in the next lectures, your homeworks and everything, as well as your projects, right? So major OS components is processing and threads, CPU scheduling, I/O management, and memory management. These are, again, the core things. OS may have many more stuff, right? So a process, when we talk about the process and threads, is a program in execution, right? Basically, the core of a process is just a piece of code. You remember when we talked about the code and CPU, right? The CPU doesn't know what a process is. It just runs. That which the CPU runs is called a process, right? So this, for example, is, we can think of the CPU as a person that just does whatever it reads, and then the pasta, recipe would be a process because that stupid person just runs it, and then your result is pasta, right? So, the input data obviously is, in memory, and these are the instructions. Hopefully, it's written in a language that the chef understands, right? And then the process can be interrupted, as we just said, right? It can be interrupted. And for example, something came up here, and then now another recipe is given to the CPU. Obviously, the task is different. It's not even in cooking, but now first aid. So get the first aid, check pulse, clean, using alcohol, apply Band-Aid, right? Again, the CPU is doing it. But now when this task is done, we want the CPU to be able to just go back wherever exactly it left off, right? Hopefully, we have not burned the food. We're not talking about, these things, but so in order for the CPU to go back to here, we understand that there is a need for a couple of other things beside just the recipe, right? We want the CPU to be able to maybe write, and memorize where I was, right, before jumping to the other thing. So these are also will be in your process control block. We're going to talk about that next lecture, right? So process and threads, they give you the illusion of parallelism in your computer. We're talking about a single core computer here, right? We're not talking about multiple core, like hyper threading and everything, right? This is a simple core. In a simple one core computer, you time share your task. Job 1, job 2, job 3, job 1, job 2, job 4, and you do this with such a high frequency that when you look at outside, you see process 1, 2, 3, and 4 progressing at the same time, right? And that's how basically, even with older computers, you get to run, play music on one side and then do something on the other side. This is just like, it gives you the, interactive. Because that each process that you request, it responds very shortly, so you actually don't feel that it's just like, frozen. And so regarding the processes and threads, OS has some responsibility. It creates and deletes processes and threads, right? This is the responsibility of operating system. Users can ask OS to do this. The OS suspends and resumes processes and threads and schedules them. Again, this is the responsibility of OS. Threads, processes, they don't have no control over this. They might actually have sign an agreement with the OS. Hey, I'm a very high priority process, or some of these, but it's eventually the OS that does it. The OS provides mechanisms for process synchronization. If you have multiple threads or running at the same time within a process, and one is doing one job, the other one is doing one job, this one wants to wait for the other one, or this one wants to signal the other one, I'm done with this. These are all happening using the tools that the OS provides, right? And it provides mechanism for inter-process communication. This is also between different processes or users. Basically, they cannot violate each other's, spaces, so they use OS to communicate to each other. The OS provides mechanisms for deadlock handling. This is again if two processes are waiting for each other, they're not like they're at the door and say like you go first and you go first and you go first. This can go on because they don't get bored unlike us. So this actually goes forever, and that's called deadlock. And so OS should basically prevent that or handle that. All right. So this is regarding processes and threads. Now CPU scheduling is very important because remember we have one CPU, we have like so many jobs. So how and when which process should run on it, it is the responsibility of the OS. And so each process changes its state during execution without knowing. Again, remember that the pasta recipe doesn't know if it has been interrupted. But the OS basically stops the CPU. So a new process is created, and then it will be ready to put in the queue. And once it is assigned to the CPU, and the CPU is basically running that, we call it a running. So in a single core, we only have one running process or thread at most at a single instance. And then other processes should be waiting for I/O. Like if a process is waiting for a signal or an I/O or something, they won't be scheduled just because they don't have anything to do yet. They have to wait for something to occur. And then once they're done, they will be terminated. Again, this is happening. OS does all of this, right? And so remember, quick question: what was OS itself? What's that? Go ahead. Yes, it is. It's a software. The OS itself, remember, it's a software, right? So again, OS does not do it by being smart or handling something out of the place. No, the OS itself is run again by the CPU. So it's kind of like it will be interesting when you actually read the code, the Pintos codes, and understand how it does it. Which part of it is now your operating system code, which part of it is the user. But it's as if that machine that I just showed. When an interrupt is happening, the first instruction that is read is an OS instruction, and that loads other instructions in interrupt vectors that, hey, go ahead, and this is like OS code. Again, CPU is running this. Go ahead, run this algorithm, understand which process should be scheduled next, okay, provide the process as it should be on the memory, and then just vanish, let the CPU run this. So and then when next thing happens, again the code of the OS comes. Again, it handles all this as instruction. It basically treats the other processes as data, right? Because those processes are processes when they run on CPU. But when the OS code is running on CPU, those instructions, they're just like on memory, right? They're data. The OS doesn't care. I mean, it cares, but. So it handles that on memory, and then again points the CPU to, hey, follow up here, and then just goes away, and then the CPU runs, right? So we'll understand this more in later. But this is also responsibility of OS. So any questions so far? Just raise your hand. Yes, go ahead.
So what was the difference, going a little bit back, but between process and thread?
We'll understand this in the next 2 lectures. Next lecture is processes, and the next one would be threads. There are subtle differences in the concept, but generally speaking, process is an entity that runs, in a space, and it does a job and everything. So a lot of the things that we talk about now is basically a process, right? Different processes are separate and isolated, and they have their own space, they have their memory and their instructions, right? A thread is basically an entity within a process. So within each process, you might have different threads doing different things, but all under the same thing. So for example, we'll actually talk about it later, right? But if you have like 2 chefs still making pasta, these are 2 threads of the same process. Right? They can communicate with each other, but they have access to each other's, the data which is shared. Some of the processes is shared. But a single process with a single thread, basically, you can use them kind of interchangeably. All right? So scheduling responsibility we kind of covered. The OS decides the available processes in memory, which one should be executed next. It decides how long a process should run. Again, these are all in code, but if you have one process, you can let it run. You don't have to stop it. But if you have 100 ones, you have to probably intervene faster and ask them to switch. It handles the external I/O interrupts, and if a keyboard comes, maybe it needs to load something else. Maybe it needs to do another piece of code. So this can change. The scheduling is also an algorithm only. So the OS runs this algorithm based on the current state of the machine, based on the waiting processes, number of processes, and other things. And then it will decide, okay, here is the process that should be run next. I'll put it there and ask CPU to go. So it has different criteria to optimize CPU utilization, to be fair among different processes and all. And it should kind of control latency. It should, like, once a new process has been submitted as a new process, you should not wait for so long. Maybe it's very small and you just should handle it really quick. So these are different criteria of process, and most of it, again, we're going to talk about in the scheduling lecture. But just remember that this is multivariable. So I/O management is another thing that the OS does. Do you have any question in the previous threads and processes first, before going for I/O? Okay. Most of these topics, by the way, will be covered in depth later, right? Again, this is just a bit of a background in the OS. So the I/O have, might have different layers. So you have actual hardware. The hardware has a piece of controller code inside it. And then there is a means of communication, which are different ports. For example, you have USB, you have parallel, you have serial, whatever. You have SATA. And then these communicate with some printer driver code within your computer. These codes are within your kernel, within OS, right? At this point, the users should not have driver controllers anymore, right? They only communicate with OS, and then they ask, hey, I want to write this to hard drive, or I want to get the image from the camcorder, and then the OS uses these codes to do this, right? And there are some very dependent code. So this code is only for Sony, for example. This code is only for Panasonic. There are different drivers, and then some are independent software. So whatever that the driver is, give me the raw image of the camera, and then I can, I don't know, do something and then give it to user. Or different printers, you can communicate with them. I want to write this character, but this character is like these pixels, but how these pixels will be actually put out to the printer is now dependent on. Okay. So you have also queues, which is again handled by the OS. OS has a scheduling queues. I have all these processes that I want to schedule in one after another, schedule on CPU. But they also have I/O queues. So for example, these processes are waiting for the disk. So why is it required? Can anyone tell me just an idea? Why is this queues required? I'll give you an example. If I want to keep what processors are waiting for the disk. Yes?
They can't use the same space and memory at the same time?
They can't, or they can?
Cannot.
They cannot, yes. But why do I still need to keep this queue?
If one relies on another.
Hmm?
If one relies on another.
If one relies on another. So that would be in the process intercommunication. But the purpose of this, for example, is that usually I/Os take long, right, relative to computation. So if the disk is now, supposedly the disk is writing, right, and that process is waiting for it, right? So when the disk is done, the CPU, the OS gets to know, okay, the disk is now available. I can do, more things on the disk. What do I need to do, right? Then it needs a queue of different processes that are waiting to, write or read from the disk. So quickly it can go to this instead of sweeping through all the processes. Because otherwise, the OS needs to go through all the processes. Do you want to do anything with the hard disk? Do you want to do anything with the hard disk? It's available, you sure, right? Advertising. But that would take a long time, if you have multiple, processes. But if you have a queue, you already know who's next to, write to disk. If this is done, who's next? Quick. All right. So you have two methods of using I/O. One is synchronous and one is asynchronous, right? So synchronous communication is when things are happening at basically, kind of at the same time where they're synchronous, as it suggests. So the control returns to the user program only upon I/O completion. Meaning, if a user or a process, basically, when we say user, wants to do something on the hard drive, it is waiting for the hard drive to be done. So it will only get to run again once that is done. And we're going to see it in a picture in the next slide. It should wait loop until next interrupt. Again, because it's waiting for the hard drive, it should just wait for the hard drive. At most, one I/O request is outstanding at a time. No simultaneous I/O processing for the process, because once it is waiting for the hard drive, it cannot at the same time wait for another thing, right? So this is an image for this. So a user requests to use a hardware. This request goes through the kernel, and this is now on hold. It's waiting. Now the hardware, the kernel might do anything, in the meantime. The kernel might, schedule another process. But this single process is still waiting until this is done, and then control gives back and then say, hey, your read is done on the disk. Here it is. Go ahead, do whatever you want to do with the data, right? Because in the meantime, I guess you couldn't do anything with it, But there are other means. So asynchronous is not that. So control returns to user without waiting for the I/O completion. Operating system communicates the completion of requests through a signal callback separately, and then a process can run while the I/O gets finished. So, for example, when you want to send a message to Wi-Fi, right? At the same time you're playing a game or something, right? You don't want the network and the internet and everything freezes your game. You send the packet, the OS will say, hey, I gotcha. I'm going to send it over the network and let you know what happens, right? You can go ahead. You can still be interactive with the player. You can, load images, whatever, and I'm going to let you know. If it doesn't happen in a minute or something, the process might say, hey, what happened? Send it again. If it comes at a different time, it handles that through a callback, right? So it says, hey, write this to disk and let me know. And then the hardware says, okay, I got the data you wanted. Go on with whatever you want. And then I'll let you know. So once that is done, it will let it know. It's just like two different means, right? If you don't want to necessarily wait for that hardware, usually this is obviously better for the process because they can go ahead.
Will an OS typically implement one or both of these?
Come again?
Will an OS implement one or both?
They're both. It's the means of communication between the user and the kernel. When the user says, I want to wait for this, then the OS won't schedule this process anymore until that is done. Right? But if it says hey, do this and let me know, it will, return the process. It might also get scheduled, back and forth, but it progress through the time. And then once it is done, it will let it know. It has probably recorded somewhere that once this request is done, which process I should notify, and these are all both implemented basically. We're talking about a modern, OS. Maybe one specific OS only implements this one, right? But generally, because they have their own uses, both are implemented. Any more questions? All right. So interrupt handling is another responsibility of the OS. The OS handles the interrupt. When an interrupt comes out, the OS, I just showed you, right? When it just brings kind of like hardwired during the boot up and loading procedure. You might get a peek of the code of Pintos for that. What is the interrupt vectors? So you basically have some hard-coded just agreements. So the CPU, whoever manufactured that CPU, Intel for example, says that, okay, whatever happens, if a division by 0 has happened, the CPU doesn't know what you want, right? The CPU will jump into this address and start running. That's it. I manufactured this. This is it. If I end up, I don't know, if power fails and a trap signal comes, then my CPU that I designed will go at this specific address and starts running. So now, as an OS designer, you will prepare instructions on these specific addresses, right? So to do whatever you want. So an OS design, okay, what if happens if a user wants to divide by 0? I have to close that program because that program is not running well, because that's not supposed to happen, right? So the OS writes a piece of program here that, okay, if this is happening, this instructions are OS instructions that, okay, look who has, initiated that addition or division, basically, that has caused this, and then do these to close that process and reschedule another process. These are all the instructions of the OS, right? So this is the interrupt handlers. You will see you will definitely work with the timer interrupt handler in your Pintus project 1, okay? That I just made an example. If a millisecond has happened, the OS should do something. What is the time now? If another millisecond has happened, what is the time now? Is it time to do something? Those are the interrupt handlers. And so, yeah, this is just an image when an interrupt comes, user process execution and an IO interrupt processing. So basically, a user is the CPU is running a user. When the IO is done with the transfer, it issues an interrupt. So the CPU goes into interrupt execution. They're usually very short, and that's when it's done. It comes back to the user, and then now the process itself may issue IO request. That IO request will, utilize the IO. Once this is done, it will interrupt. Again, you will run an interrupt handler, and again back to the user, right? So this is what has happened. This is just what I said. The CPU keeps running. Once it issues an OS, it goes to the IO controller. IO controller initiates IO. It may take some time. It's just CPU is still running. But in the IO, when it's done, it will generate an interrupt signal. The signal goes to the CPU, goes to the interrupt handler. The interrupt handler decides what to do with that signal, what is to be done. Should I wait? Should I wake another process? Whatever that needs to be done will happen, and then CPU resumes the process. Right? Any questions in IO? No? Yes?
So if you had some catastrophic error in a program that causes it to close down, that last step, CPU resumes processing of interrupted time, is that necessarily going to happen?
So at this point, it might decide that, hey, it's not time to resume the same process. I will close this process and resume another process. That's the scheduling algorithm that basically decides who should resume. Maybe the same processor, maybe same process, maybe another one. Good question. You actually might deal with that in project 2. Yes?
What happens if you error?
What error?
Like blue screen.
Error handling is also there. So if that's usually when the OS itself crashes. OS is not perfect. Maybe the OS itself crashes, and if you close that program which has issued the error, and if it's OS, then your OS is crashed, right? So if an IO errors, that's fine. That can be handled. So for example, I want to send a message through Wi-Fi, right? It returns with an error. I couldn't send it. The OS says, okay, send it again, right? If it's the third time and you tell me that I couldn't, then maybe there's something wrong with the network. Then you load up some network manager software or service that, hey, and then shows you the signal in the Wi-Fi that is not connected to anything, right? These are just like normal processes. These are not catastrophic errors. And that's called error handling. If you don't handle an error, it can cause a catastrophic, error as well, right? So you have a division by 0 in a software. If you divide by 0 and you don't handle it, then your program just, exits, shuts down, right? But if you handle an error, divide this by this, catch the error in this case, and then your OS says, okay, I should still resume the rest of the program. So OS responsibilities regarding I/O is that it hides all the complications and peculiarities of the specific hardware devices from the user, so the users don't have to deal with them. OS issues the low-level commands to the devices and catches interrupts and handles errors, and relies on software modules called device drivers. These are part of the OS, and provides a device-independent API to the user program, which includes buffering. Again, if you want to send something over the network, which network, it doesn't matter, but just like have a buffer. These are the things that you want to send. That's the buffer. All right? So this is memory management. Memory needs to be subdivided to, we're going to talk about memory a lot, so I'm going to briefly go over it. So memory is an optimization task because you have a limited memory and so many processes. Each of them want their own unlimited memory. You can't have all of this. You have different means of memory. You have registers, very small. You have some cache, You have main memory, which is like maybe some gigabytes. You have solid state disk or hard drive, which is like in order of terabytes. You have magnetic disk. I mean, maybe you don't, but you can. Which is used for storage and backups, right? And then how and when, what to load and move between these, because you don't want the CPU or process wait for this, right? That will take, seconds and minutes. So when to do these, and these are all the things that the OS should do, right? So the OS keeps track of which parts of memory are currently being used and by whom. So in case a process wants to shut down, you want to free up and clean after them, so that piece of memory will be available for others, right? The OS allocates and deallocates memory space as needed. If a process wants to load something, they would ask for more memory. The OS, gives them the memory so they can use or reverse. The OS decides which processes to load or swap out. That's moving between the different, memory devices. And ensures process isolation. That is very important. You don't want processes to have access to each other's data. There's always, you hear all these attacks and, bugs and issues. But right now, they're pretty okay. But still, sometimes they're... So at some point, for example, even if the OS doesn't actually clean out and say, hey, okay, here it is, and this is available, there used to be programs who would load, and then before doing anything, they would actually look for what the previous process had there, right? And that was that was attack. That was a kind of an attack because they could access some data, maybe whatever. And so one of the processes responsibility of the OS is to actually clean, make sure everything is 0, for example, before loading. OS regulates how different processes and users can sometimes share the same portions of the memory. Those are the shared pieces of code or data. Transfer data between main memory and disk and ensures long-term storage. That's kind of says what it's here. Where is that? Swapping, but separately, it's also when you want to save. All right. So the OS design approaches and there are different approaches. So you have different goals, right? You have to define them, and then they are affected by the hardware type of the system. What you want to do, you are in a batch, time shared, single user, multi-user, distributed system. These are all things that can vary between systems. And your goals might also be different. So users want their operating system to be convenient and be easy, fast for them. And the system goal wants to have ensure the security and error-free and reliability and all this, right? And because of all these different criteria, you can't have a unique solution, right? And that's why you have different operating systems, right? Mac OS is really cute and it's easy. It's usually error-free and reliable. But on the other hand, it has, lacks a lot of things. Windows crashes, but it gives you a lot of flexibility. Same goes with others, right? So it's important as a principle to differentiate between policies and mechanism, right? So you have a policy to say what should be done. I don't care how you want to do it. It's a policy of the campus, right? And then your department will implement it. That's the mechanism. How will it get done? How can I ensure that students don't register for extra credits, whatever. So this is also in the OS. OS has a policy that, hey, I want this scheme of a scheduling, and the mechanism is the actual algorithm implemented. This gives you the flexibility of, maybe you want to change policies later. If you have the means of, the mechanism, then you can change the policy. This is another example. So we have different design approaches. We have a simple structure, we have layered structure, microkernels, modular, and hybrid systems, right? So the simpler structure was just when they didn't actually plan for it, right? It was not defined. It started as small, and then it grew. And then, for example, it's the MS-DOS. At that point, the systems, again, did not mean to have operating systems, so the hardware was not ready for it. That's the user kernel mode. CPU does not do some things in the user mode right now, so user codes basically cannot harm some devices. At that point, they didn't, so they had a complete control, and that's why the MS-DOS also didn't predict this and didn't plan for it. So it was kind of very terrible, right? So when we decided to go to layered, they decided to basically separate and make different layers, so it doesn't actually go around the OS and then access the hardware directly, right? They want it to be a separate layer. So the monolithic operating systems, they did not initially had the experience of building large operating systems, and the problems caused by mutual dependence and interactions were grossly underestimated. Again, they didn't know. They were just like rookies, right? Newbies. Such lack of structure became unsustainable as OS grew, and that's why I think Unix is a monolithic. Early Unix and Linux and Windows systems were monolithic, and that's why they crashed a lot, right? Because they were not prepared for such stuff. They were like a lot of code crammed, and then they entered hierarchical layers, so we can well-defined layers and have more layers to have an organized OS. This was the abstraction and idea, so that each layer is implemented upon the other one, and it just deals with the layer below and above that, and the layers should be simple, right? So the simple layer approach, the problem is that the big mess, a collection of procedures that can call any other procedure within the kernel. You have a big kernel code, everything is here and everything has access to everything, and everything can call everything. The problem, it ensures a bit of a layer here and a here, but itself can have a lot of issues, right? And so you have visibility, so you have vulnerability, and you have minimal layering, so you have a lot of crashes or freezing, right? So a fully layered approach says, okay, I'm gonna do it like this. So layer number 2 should not have access to this or this, only to the layer above and below. So there were some OSs like that, and I guess, but you don't see them. The problem is when you want to have layered approach, for example, like TCP/IP, you should be able to define what each layer is. The network layer only takes the link layer and then services the application or transport layer, right? So TCP is using IP, and the IP is using either Wi-Fi or Ethernet, whatever. So it's kind of well defined. The problem, and that makes it easy to swap each layer, because you know what it needs to be done, what it needs to do, and what it has from the lower layer. So then you can replace this layer. But the problem is how to define various layers. How to exactly define various layers. That's one issue. And the more layers, the more indirections. A function calls another function, and that calls another function, that calls another function. This adds overhead, right? And then what happens if you want a circle or a dependency that is not completely directional? What if for some reason your lower layer wants to have access to something in the upper layer? You can't completely make them directional. So these are the problems. So microkernels decided to basically take only the essential OS cores in the OS, and everything else push to the user space. So device drivers, file systems, virtual memory manager, the GUI, all of it pushes up to the user, and only the scheduling, message passing, and some core things in the OS will be there. So CPU scheduling, memory management, inter-process communication. This will be the minimal kernel, everything else in the user's mode. So this doesn't crash. This is one of the good things about it, right? So the pros is that it's easier to extend a microkernel. You can add different modules or run programs. It is portable because you can just port it easily to the other computers or hardware. It's easier. You don't have to make many changes. And it's reliable and secure because your code, if crashes, then you can your kernel doesn't crash. You can reload that process, your network manager. It doesn't matter. So the cons is that performance overhead, because everything has to have message passing through the kernel, and this causes a lot of overhead and delay. So that's one of the cons. And this is always not realistic because some functions must remain in kernel space to have access, right? It's just it's not possible, practical basically. So then we have modular, which within the kernel, you have modules. They're not in the user space, but they're separate modules in the kernel, so you kind of divide and isolate them. So in Linux or Windows, Mac, and then these new ones are usually like this. They have benefits of each, but they have also flexibility. So they talk to each other through the known interfaces. They have dynamically loadable modules within the kernel, but because they're isolated, they don't necessarily freeze up that much. And modular is still similar to microkernels because they're separate, but they have their own access as well, right? Instead of like message passing, they have direct, communication. So this is some benefits, but that's why still they sometimes crash, right? And so this is modular. And then we actually have like hybrid systems. So the actual systems, they like Linux is a combination of monolithic and modular, right? Windows monolithic, microkernel, and modular. Mac OS is microkernel and modular. So again, a hybrid, because that's the functionality is important, right? So they want it to work. So for next session, please read the Pintos manual introduction. It's only 8 pages. Appendix A1, which is only 3 pages. Start your VM and then look around the source code of the threads and finalize your groups by the end of the week. All right? Any questions? Yes. What's that?
How do we finalize our group? Can we send you something?
How do you finalize the groups? I will let you know. We will register them in the auto grader.
Okay.
All right? Awesome. See you next session. Let me just hold on a sec. I'll stop this.